In the last video, I suggested that when you breathe in, you're breathing in a volume Vt. And when you breathe out, you're breathing out a volume Vt. And actually, it turns out that that's not quite true. And I'll write that there so that you don't think it is. Not true. So to understand why, let's look at our simple model of the lung. This lung is filled with some gas, but we're not going to worry about that gas and whether it's oxygenated or deoxygenated. This time we're going to talk about water. So let's say you pour a little bit of water into the lung here. You have some water molecules floating around in there, and you probably remember from intro chemistry that every once in a while, one of these molecules is going to fly out and become a gas. And so you're going to get some water gas up here floating around. And that's going to continue, but it's not going to continue forever because these gases are flying around, ricocheting off the walls pretty fast, and every once in a while they're going to go back into the water. So this situation will reach an equilibrium when the rate at which molecules are going into the water is the rate at which they're leaving. And this equilibrium is reached when the partial pressure of the water gas, which I'm drawing in green so that you know exactly what I'm talking about, is equal to the vapor pressure of the liquid. And that happens to be 46 millimeters of mercury. And you're probably wondering where that came from. Well, that just happens to be the vapor pressure of water at body temperature, which is 310 degrees Kelvin. And you might be wondering, well, are these molecules going to sort of diffuse up the tube and go out into the outside world? Well, you'd be right, they probably will a little bit, but let's just assume that this tube is kind of long and skinny, and so it'll take too long for the water to diffuse out. So we'll consider that it's kind of separate. Now we're going to look at what happens when you breathe in. So let's say you inhale. And you probably remember that when you inhale, the size of your lung is going to increase, and that's going to pull in some additional gas. So here's your expanded lung. And just to be clear, you probably remember from last time that the volume of this circular thing was Vi before you inhaled, and then it became Vi plus Vt, because Vt was the total amount that you inhaled. And the volume of these sort of tube-like things was Vd for dead volume. But we still have our water here at the bottom of this lung, and we have our water molecules floating around there, and the temperature of the lung is the same, so the vapor pressure is still 46 millimeters of mercury. But when we look up at the gas that's here, at the water particles of the gas, they're spread out more than they were. So actually their partial pressure has decreased. And although they're still flying around at the same rate that they were before, there's actually going to be less of them going back into the liquid because their partial pressure is now less than the vapor pressure of 46 millimeters of mercury. So we know what's going to happen. Particles are going to join the gas until this is no longer the case. So there's going to be more water in the gas than there was before until the partial pressure of the gas is equal to 46 millimeters of mercury again. And just so we're clear, we're still assuming that this sort of tube-like structure is kind of too long and skinny for all these water molecules to diffuse out into the outside world. So here comes an important point. These tubes, although they're too long and skinny for these water molecules to diffuse out, they do connect these lungs to the outside world, and therefore the total pressure inside the lungs will be the same as that of the outside world. And we know that atmospheric pressure is 760 millimeters of mercury, and so that's what the pressure inside the lungs is going to be, 760 millimeters of mercury. And I'm drawing it in white because it's the total pressure. It's not just the pressure of the water. It's the pressure of the water plus the nitrogen, plus the oxygen, plus the carbon dioxide, whatever else is in there. And now we're ready to answer the question that we posed at the beginning. Why is it not true that what you breathe in is equal to what you breathe out? The reason is that the water that's coming out of the little puddle at the bottom of this lung takes up space. So let's be a little more concrete and look at some numbers. Your average tidal volume is about 500 milliliters. which means that on average when you breathe in and out, your lungs are expanding by half a liter and then contracting by half a liter. So of that, how much of that volume is made up of water? Well, it's equal to the total tidal volume times the fraction of that total tidal volume that's taken up by water, which is the partial pressure of water over the total pressure of the gas. And this equals about 30 milliliters. So let's go back to our little guy breathing and let's fix this error that we made in the last video. What's really happening is that you're actually breathing in only about 470 milliliters of air, and then you're breathing out 500 milliliters of air, which includes the water vapor that your lungs kind of produced. Finally, you might be wondering, well, we don't actually have puddles of water in our lungs, so where is all this vapor coming from? Well, the body is a very moist place, and we're all made up of about 70% water, and so it shouldn't come as too much of a surprise that your lungs, your bronchi, your trachea, everything is kind of coated in moisture. And so that moisture kind of sitting around is where the water vapor comes from. Now this might strike you as strange, because if we're breathing out an extra 30 milliliters of water every time we breathe that we didn't breathe in, aren't we losing net water? And the answer is actually yes, we are. And so the last thing I want to do just for fun is to calculate how much water we lose every day just from breathing. So let's scroll down to give ourselves a little bit of space. So we've decided that we lose 30 milliliters of water vapor every time we breathe. So if we multiply that by our respiratory rate, that'll tell us about how much water vapor we're losing per minute. So the average person breathes about 15 times per minute. Now to find out how much water vapor we're breathing out per day, let's multiply by 60 minutes per hour and 24 hours. So this here is going to tell us the volume of water vapor that we're breathing out every day. But volume of water vapor probably doesn't mean much to most of us, so let's find out how many moles that is. We know that for a gas at STP, standard temperature and pressure, there's about 22,400 milliliters per mole. So let's divide by that. And now we have this big term which is going to tell us how many moles of water we've breathed out per day. But moles don't mean much to most of us, so let's multiply this by the molecular weight of water, which is 18 grams per mole. And this gives us an answer we can do something, which is approximately 500 grams. And that's not insignificant. That's about 1 liter of liquid water. Most of us drink about 2 liters. So based on this calculation, we breathe out about half of all the water that we drink. So in closing, I'll just scroll back up so that you can look at this picture again if you want.